Okay, good evening, everyone. Hope you're all doing good. Right. So again, next week's class. So it's been a week since we met. Right. So I hope everything is going good. So did you all go to school? Did you meet your friends?
Yes, sir.
Good feeling, right? After a long time, meeting them physically, hang out with them. Nice feeling, right? So, did you find any difference after a long time? You would have been actually attending offline classes in school. Like, was it good? Anything different you felt, or it's the
Not
same old,
really,
same
sir.
old? No, sir, it's the same boring stuff. They do in online, they do offline. Like either way, it's boring, right? So, anyways, how many people we have? We have 8. Maybe we'll wait for 1 or 2 more minutes for your friends to join, and then we'll start. Right.
Sir?
Yeah.
Sir, if you had remembered, I had asked you about how do we find the volume of an atom or any subatomic particle.
Yes, yes.
Sir, so I thought like we have read right like the size of an electron or size of proton. So does that mean it is the diameter?
They're talking about the volume. When they say size, they always talk about the volume.
Sir, I didn't
Yes.
understand. Can you tell again?
Like whenever they speak about the size, say when they say that compared to the size of nucleus, right? When I compare it to the size of electrons size are negligible. What do you mean by size? Size is nothing but the volume. And how do they calculate volume? They generally consider them to be spheres. So as you said, say the radius or the diameter, say it's no, you know the formula 1/3 pi r cube. That's the thing they use for calculating the volume.
Yes, sir. 4/3.
4/3. Yeah, that 1/3 is for hemisphere. Correct. 4/3 pi r cube. Correct. Yes.
Yes, sir. Okay.
So that's what it means. Anybody has any other questions regarding the previous classes? Did you go through, guys? I think there is so much noise here. Anyways, so I think I already spoke about this, right? So okay, right. So I have already spoken about this. I don't know how many of you are taking notes, right? I don't know about any other class or any other faculty, their style of teaching and stuff. But for my style of teaching, right? For my style of teaching, it is really advisable that all of you take notes, right? You must be in constant touch with, whenever I teach, you must be looking at the video and you must be constantly taking down notes somehow, right? If you're not able to do that, then watch the recorded video, right? Watch the recorded video in say 2x or 3x, say fast forward it and then take notes. But that would really not be advisable whenever the live class is going on, right? At that time, it is really advisable for you to take down notes. Just record whatever comes out of my mouth, literally whatever comes out. Not I mean with respect to chemistry, obviously, with respect to science, right? So it's always a good habit, because why I tell you that is, say I teach you, you don't take notes, and obviously the only other choice you have is to go through your textbooks, right? Now textbook reading, that big chapter like equilibrium, chemical bonding, all these are very big chapters. You going through that book only will make you sleep, right? But if you have taken down notes, say a 10-page 20-page chapter, you would have been able to cut down to, like you will be obviously writing it in a way in which you will understand, say the arrow mark, say coming like this, something whatever way you understand, right? So for you to go through that, if for the entire chapter in the book it takes say 2 hours, here you will be completing another half an hour itself, right? The entire chapter half an hour done, right? But obviously for that to happen, you have to put some efforts and take down notes. I don't know how many of you take it down, right? I think last week I spoke about it. Valence bond theory I asked, nobody was able to answer because you didn't take notes. It was very obvious, right? So please do start it, right? If not, at least have a, like, I don't know, it's a shortcut. Have a friend who actually takes notes, right? But again, like that person should again be, generous enough, right? For he or she to give you your notes, because they have taken down the efforts, right? So if they deny, saying that no, I cannot give you, you cannot question them also, right? So it is always better to take down your own notes in your own way possible, right? Okay, so with that being said, let me start my class. I will share my screen. Okay, so India, England match is going on. I was watching that. Anyways, okay, let me go to one. Okay. Fine. So this is 11th. Today, I think is 4th. Today is 4th, right?
Yes, sir.
409. Okay. Fine. So we have been looking into this theory of hybridization. Actually, what we'll do is we'll have a very quick recap of the previous class and then we'll come back here. Okay. Because we saw a lot of things last class. Is this the thing? No, right? It's 28, 11, 29. Yeah, I think this is the thing. Yeah, this is the thing. We saw a lot of things last class, a lot of important things we saw. Okay, so someone's asked about the nodes, so it was that. Okay, so we started with this theory of hybridization, right? So we said that how is an hybrid orbital formed? An hybrid orbital is formed by mixing or combining two or more atomic orbitals, right? And remember that the hybrid orbitals, say the atomic orbitals we're talking about, right? The atomic orbital should come, all the atomic orbitals should come only from the central atom, right? So this is the basic difference between hybridized orbital and orbital overlap, right? Say when I say two orbitals are getting overlapped, right? Obviously the result would be a pi bond or a covalent pi bond or a sigma bond, right? So when two orbitals overlap, either head-on collision is your sigma bond, lateral overlap is your pi bond, right? Now there you see where the atomic orbitals are coming from. One atomic orbital of one atom and the atomic orbital of the other atom, right? Say H2 molecule, two H2 molecules, S orbitals are the one which will come together, overlap and make a sigma bond, right? But here you check, in case of a hybrid orbital, the atomic orbitals you see are going to come from the central metal atom or central atom only, right? That is the main difference here. And obviously, the obvious point to be noted is that the number of hybrid orbitals formed should be equal to the number of atomic orbitals combining, right? That we saw. Okay. And next thing what you have to understand is the atomic orbitals which are combining should be of similar energy. You cannot combine 2s and 3p, right? You can combine only 2s and 2p, or say 3s and 3p and 3d, like that, right? They should be of similar energy, right? Okay. Then we saw what are the different types of hybridization I can have. I can have sp hybridization, sp2 hybridization, sp3 hybridization, sp3d, sp3d2, sp3d3, depending on how many number of s orbitals, p orbitals and d orbitals are combining. For example, if in an sp hybridized orbital, I can easily understand that there is going to be one s orbital and one p orbital. Again, one number of s orbital, one number of p orbital, right? Okay, so now even it can be 2s and 2p. 2s and 2p, I'm talking about the orbitals are named, right? One 2s orbital, one 2p orbital can combine to form sp hybridized orbital. And how many numbers of sp hybridized orbital? Again, that is coming from nh equal to na, right? That is, since two atomic orbitals combining, I'll form two numbers of hybridized orbital. In this case, the hybridized orbitals are sp hybridized orbitals, right? Same way in case of sp2, I will have one s and 2p. Again, this 2p is not the name of the orbital, people. It is the number of p orbitals, 2p orbitals, right? Well, I will come together to form three numbers of sp2 hybridized orbital. You can see three numbers, three boxes. Here it's two boxes. Same way for sp3, you'll find four boxes. For sp3d, you'll find five boxes, and so on and so forth, right? Okay, now again, as I told, all these hybridizations, right? All these hybridizations are going to happen only for the central metal atom, right? So when I say a sigma bond, I can mention here a sigma bond is formed by overlap of hybridized orbital of the central atom with the atomic orbital of the side atom, or say the bonding atom. I read Ba. Ba is the bonding atom. So I'm going to have
Sir,
the high. Yeah, tell me.
sir, can we say that the central atom is the least electronegative atom in the molecule?
Yes, obviously. I told you, right? When how you choose a central metal atom, right? Say if you have confusions, right? Obviously, the central metal atom should be the one which should be having the least ionization energy, right? Because central metal atom is the one which is going to share maximum number of electrons with the bonding atoms. For example, in this case, say you take S sub 6, this molecule you take. Obviously, sulfur is the one which is sharing 6 electrons with fluorine atoms. Each of the fluorine atom is sharing only 1 electron. That's fine. But the central metal atom is the one which is sharing a lot of electron. Obviously, the ionization energy should be very less. Obviously, the electronegativity should also be very, very less. Okay, so the least electronegative atom is the one which is going to be the central metal atom. Obviously, that works. Right? Okay. Right, good. So now what we understand is how a sigma bond is formed. Yeah, question?
Sir, can you once show that hybridization of 2s and 2p?
Okay, this is S and P, right? Yes.
Yes, sir. So when we combine S with P, we get Sp. And when we combine 2s plus 2p, we should get 4sp or 2sp.
No, that's what I'm telling. See, first of all, there is no orbital called as 1p, correct? Right. So
Yes,
now
sir.
when I say 1p, I'm talking about number of p orbitals. How many p orbitals are there? I'm talking about one number of p orbital. Right. But when I say the hybridization is happening between one of the 2s orbital and one of the 2p orbital, again, one orbital here, one orbital here. Still, I will be forming sp hybridization, but again, two numbers of sp hybridization. That's it. And these sp hybridization is formed by the 2s orbital and the 2p orbital coming one orbital each. Right? Please do not confuse yourself between the number of orbitals and the name of the orbital. Do you get the point?
Yes, sir.
Okay, please do not confuse yourself. Here it can be 3s, it can be 3p, it can be 4s, 4p, and these are the numbers which represents the name of the orbital.
Sir, 3s is not possible, right?
Why 3s is not possible? I'm talking about the name of the orbital.
Okay, sir. Yeah.
Okay, I hope you understand, right?
Yes.
So now, okay. Anyways, don't confuse yourself, right? Here, what we are talking, the numbers which we are using here, 1, this 3, and we don't keep, right? Say this 2, 3, 1d, and all that. These are numbers of the orbital. How many such orbitals are combining together?
Yes, sir.
Okay.
So there are 2 orbitals of S combining with 2 orbitals of P, and the total number of hybrid orbitals should be equal to the total number of atomic orbitals. So 2 plus 2 should be 4, right?
Correct. But the thing is, how do I put it? At a time, right? At a time, I can take only one s orbital at a time. So in the sense that you are telling 2s, say I'll call you have 2 s orbitals, in the sense that 2sa and 2sb are the 2 orbitals. 2sa is one of the orbital and 2sb another 2s orbital. Right? Now like this you cannot take. Why you cannot take is obviously because there's only, at a time I can have only one s orbital coming. Right? Same way, I can tell that 3px, 3py, and 3pz, I can take all 3. Right? But I cannot take one 3px, say 3px, and another 3px dash. I cannot take these two together. No. Do you get the point?
Yes, sir.
Okay, you can take from the same, hope you understand, from the same subshell, I can take the orbital. I cannot take two different atoms and two different subshells and two different p orbitals. No, I cannot mix them like that. Okay, right? Anyways, if you see more if you see more examples, you'll get more clarity. Anyways, what is the question?
Sir, then what is the number of orbitals for 2 number of s orbitals plus 2 number of p orbitals?
There is no hybridization like that. There is no hybridization.
Okay, so it's only 1 2s and 1 2p.
1 2p, or say 1 3s and 1 3p, something like that.
Okay, sir, got it.
Okay, right? So hope you all get the point, right? please do not confuse between the name and the numbers. All we need for the hybridization, I don't care what is the orbital's name. I just care about how many atomic orbitals are coming. That is all I'm worried about. Right now, that is taken care by this statement. The other thing, the name of the orbital is taken from this statement, in the sense that the atomic orbitals which involve in hybridization should be of similar energy. In the sense that, say, if you want to make sp hybridization from 3s and 3p, it's okay. 4s and 4p, it's okay. But you cannot do it from 2s and 3p. That is impossible. Right?
Yes,
Hope
sir.
you all.
Sir,
Yeah, tell me.
sir, as you said earlier, like 1p is not there. So the most correct way to write it would be 2s plus 2p, right? Like the name.
Exactly. Yes. 2s is the name, 2p is the name, and one orbital of each will combine together to form sp hybridized orbital.
Okay, sir.
Okay, right? Fine. Same way, sp2 is fine. Same way, sp2 also, it will be 2s and 2p only. For sp3d alone, obviously it should be 3s orbital, 3p orbital, and 3d orbital. In the sense, these one orbital, here 3 orbitals, here 3 orbitals. Here it's 1 orbital. Anyways, don't confuse yourself. We don't have to worry about any of this, right? Hope you're all understanding. The names which we write here, the numbers which we write here are the numbers of orbitals combining, not the names of the
Sir?
orbitals. Yeah.
So then how do we represent number of 3p?
Yeah, 3 numbers of p number, we write it like this only. But again, see, we need to have a proper notation. Say you write like this. Instead, if you want to represent 3 numbers of p orbitals, you write it as p1, p2, and p3. That's better. But if you write 3p, it can be confused in the case whether it's 3 numbers of p orbitals or say 3p orbital, the name of the orbital, right? So if you want to mention 3 numbers of p orbitals, you write like this: p1, p2, p3.
Okay.
Okay, fine. Anyways, so you all remember what are the different types of hybridizations and how many number of hybridized orbitals will be formed, right? Okay. Now next thing we saw was how, just by looking at the molecule, right? Just by looking at the molecule, will I be able to find what is the central metal atoms' hybridization, right? So for that, we went on to see what is this number called a steric number, right? I gave you a formula, right? And before we see the formula, depending on the steric number, how do you decide the hybridization, right? So this steric number is also equal to the number of hybridized orbitals formed, or say the number of atomic orbitals combining, right? So if you find that the steric number is 2, right, I can directly say that the molecule is having sp hybridization. Same way, if it is having 3, I can tell that it is going to be sp2, because you can see 1s and 2 p's, totally 3. 1s, 1p, totally 2. Right? So like that, if it is going to have 5, then it is going to be sp3d, so on and so forth. I can tell, but with the help of steric number, right? We saw examples for that. Yeah, tell me.
But only if the number of lone pair is 0, it will be the same, correct?
Only if the number of
lone pairs is 0. Then only if the steric number is 5, hybridization will be sp3t.
Not necessarily. Whether I have lone pairs, whether including lone pairs or without including lone pairs, if I have 5, obviously if the lone pairs are there, I have to include it. And if I find that the hybridization is, if I find steric number is 5, then it is sp3d only.
Sir, I understood, sir. I didn't include because already it's included.
Correct. It's already included.
Yes,
the formula itself is like this, whole formula.
Yes,
you have to include them both. Right? Okay. So in this case, we saw an example for carbon dioxide. We saw that the carbon is a central atom. Now, if you look at the formula, it is number of atoms bonded to the central atom. How many atoms are there which are bonded to the central atom plus number of lone pairs in the central atom? See, we are doing it only for the central atom. Be very careful. Right? So carbon dioxide, carbon is central atom. There are 2 oxygen atoms attached, and obviously there are no lone pairs on carbon. So 2 plus 2 will become 0. It is sp hybridized. Right? Now you see ammonia. Right? Now ammonia, central metal atom is nitrogen. Right? And you see there are 3 bonding atoms in the form of hydrogen. And obviously I know there is 1 lone pair on nitrogen, which makes it 4. 3 plus 1. 3 bonding atoms and 1 lone pair on nitrogen makes it 4. So totally it will become sp3 hybridization. Right? So like this, you can see now this is an example of having a lone pair. I'm including it in the formula itself. right? Hope you are able to understand. Right? So now we saw example for XCOF4. We saw the structure also, sp3d2 it has, right? Now, whenever these kind of molecule comes, right, you have to take one atom at a time, right? You take this as a central atom and check, okay, this side carbon atom, this side hydrogen atom. Same way for this, if you take this as a central atom, this side carbon atom, this side hydrogen atom. So if you do for any one of the carbon atom, it's fine, because in this case, I would say both these carbon atoms are sp hybridized. That's the exact way of putting it. Okay, there are two carbon atoms in the molecule and both the carbon atoms are sp hybridized. Okay, that is what we have to understand, right? And then since we took the example of NH4 plus, we went on to see the concept of what is that? Your coordinate bonds, right? So we saw multiple examples where I can write two structures, right? One with a coordinate bond, one without a coordinate bond, and both are correct, right? But sometimes chemically we'll be able to prove that, okay, this is the structure for NH4 plus with the structure with the coordinate bond makes sense, right? Because ammonia is the base, it will accept H plus. So obviously the positive charge has to go to hydrogen, and in this H plus there is no electron, right? So the two electrons will go from nitrogen to hydrogen, right? So this is a proper structure. Same way we saw example for carbon monoxide, for example for coordinate bond. So many examples we saw, right? So for SO4 2-, we saw an example with, a structure with a coordinate bond, without a coordinate bond, right? Fine. So now we saw even how this thing works. And I told you, for hybridization purposes, right? For hybridization purposes, you must always remember that when I have a positive charge, it has to go to the central atom. And when you have a negative charge, it has to go to the side atom or the bonding atom. Only then you will be able to get the correct hybridization. Okay. So in this case, I have a positive charge. The positive charge goes to nitrogen here, right? Even though chemically it's not correct, right? Say that is, we don't have chemical proof for this, but for mathematical proof for the concept of hybridization, it's better you put the positive charge on nitrogen atom so that it comes out properly. We'll take the example and see how it is sp3 hybridized. Don't worry. Okay. And then we went on to see, we went on to cases where we took particular examples, say SN2, steric number 2, we started seeing examples, right? Steric number 2, we saw the example. The first example was beryllium chloride, right? Now, hope you all remember how do you make the hybridization, people, right? Fine. So how do you do it? Is you first choose a central metal atom, right? Obviously, you know central metal atom. You check what is the hybridization from the formula, steric number, but you don't show this here. Okay, in your school exams, you don't show this step here. Okay, but you find it out. You keep it in your mind, right? The first step would be to write like this. Write the ground state electronic configuration of the central metal atom. Okay, so beryllium ground state, I'm going by atomic number 4, 1s2, 2s2, 2p0. Okay, so in the ground state, 2s will have 2 electrons and 2p will have no electrons, 0 electrons, right? Now beryllium goes to excited state. Right now, beryllium goes to excited state. Now, so this one electron which is paired goes to the next higher energy orbital. So it goes to 2p. Right now, what happens? This 2s and 2p. I know the hybridization is sp, that I know. Right, so I require one s orbital and one number of s orbital and one number of p orbitals. Right, say this 2s and 2p combine together to form two numbers of sp hybridized orbital. Right now, what has to happen? Now the overlap has to happen. Now you formed the hybridization. The next step would be the bond formation, sigma bond. And I told you, for a sigma bond to be formed, the overlap has to happen between the hybridized orbitals of the central atom with the atomic orbitals of the bonding atom. Right now you have the hybridized orbitals, sp hybridized orbitals of beryllium. Right now they will overlap with the atomic orbitals of chlorine to form 2 sigma bonds. 2 chlorine atoms will come, 2 overlaps will happen, so 2 sigma bonds will be there. Okay, right, fine. We saw, I think, another example where I have a pi bond, right? Excuse me, right? I have a pi bond in the form of carbon dioxide. We already saw this. Obviously, the hybridization is sp2, right? Now, I told you for a sigma bond, the overlap is between the hybridized orbital of the central atom with the atomic orbital of bonding atom. And remember, for a pi bond, it is always pure atomic orbitals. electrons, both of them. The overlap will be between the atomic orbitals of central atom with the atomic orbitals of bonding atom. So what you have to remember is, if there is a pi bond, right, that pi electron, what do you mean pi electron? Electron involving in a pi bond, right, should not be inside hybridization, right, should not be inside the hybridized orbitals. It must be there in the pure orbitals for central atom, I'm telling. Okay, fine. So we'll do this for carbon dioxide, then it will make more sense, right? So carbon dioxide, again, in central metal atom, you know the hybridization is sp. Do not show this in your school exam. Now you write the configuration, electronic configuration, 1s2, 2s2, 2p2. Ground state, write it. Excited state, whichever electron is paired, put it to the next higher energy. So you have this, the third electron is here, right? Now all you need is S and P, one S and one P, one number of S and one number of P. So you'll take this 2S and one of the 2 P's, you will form sp, two numbers of sp, and the normal sigma bonds with 2 oxygen atoms, right? You can see the sigma bonds which are here, say one sigma bond, another sigma bond, done, right? So now what you have to understand is the pi bonds, right? Now very simple, I told you the overlap is going to happen between the atomic orbital. This is the atomic orbital, this is the atomic orbital, right? So pure atomic orbitals will combine with pure atomic orbitals of p to form pi bonds, right? So now these 2 electrons which are here, now this electron will go with one of the electron from first oxygen, get paired, pi bond. Again, this particular electron, right, this particular electron, second electron, will go with the second oxygen atom, 1 electron, to form another pi bond.
Sir?
Okay, yeah, tell me.
Sir, can you repeat this again?
Yeah, sure. What I'm
Pi
telling
bond.
you is, right, I need sp hybridization, so sp is done. Okay, one S and one P is done. Sigma bonds are okay. These are the sigma bonds. Okay, now I have 2 more p orbitals having 1 electron and another electron, right? Say now what happens is 1 p orbital. Okay, I'll write like this. This is your, say, py, right? Now py of, this is for carbon, which is having 1 electron, say, right? Now what is going to happen is I'm going to have the py of oxygen. This is carbon, this is oxygen, and it will also have 1 electron. Now lateral overlap will happen. Pi bond, 1 pi bond, say pi 1, I call it. Right? Now this bond is done, 1 electron is done. I still have 1 more electron, say carbon, second pz orbital. Say obviously the shape should be different, but it's fine. So pz orbital, again I'm going to have oxygen's pz orbital. Again 1 electron here, 1 electron here. Again lateral overlap will happen to form the second pi bond, pi 2. Okay, so that is what is happening here. The pure atomic orbitals are the ones which are involving in bonding. 2 electrons are coming from carbon. 2 electrons are going to come from each 1 oxygen atom. 1 each oxygen atom. 1 electron each from 1 oxygen atom, and 2 electrons from here. 2 pi bonds. Very simple, right? Now the trick to remember. What is the trick to remember is this.
Sir.
Right? Yeah, tell me.
Sir, there is no oxygen, sir. This is C2H2.
No, we're talking about CO2 only. We're talking about CO2. Like here also I've written, it's the sigma bond is also coming from oxygen also, oxygen only.
Okay, sir.
Okay, right. C2H2 also will have sp hybridization only. We'll look into that. Okay, so now what is the trick to remember, people? This is the trick to remember. The number of pi bonds in any molecule, right, is equal to number of electrons, number of unpaired electrons in the central atom, and most important point is after hybridization. Okay, after you complete the hybridization, check whether you have unpaired electrons. If you have unpaired electrons even after hybridization, then definitely it is going to have a pi bond. And how many such unpaired electrons you have, that many pi bonds you can have in this in that particular molecule. So you see there are 2 unpaired electrons, 1 here, another here. So obviously you saw there are going to be 2 pi bonds. Okay, right? We'll move on to the next example. Say the next example we take is C2H2. Right? So here also the same thing. Carbon will again have the excited state, the same thing as the excited state in the previous case. Right? Now what you have to do? Again, you form I know the hybridization of C2H2. Both the carbon atoms here are sp hybridized and sp hybridized. Right? So again, the same thing will come. sp will be done. 2 sigma bonds are gone. After you complete this, 1 s and 1 p you take. Even after that, there are 2 more electrons left. Right? 2 more electrons left. which will obviously form 2 pi bonds with the pure atomic orbitals coming from. Now, in this case, the pi bond will be between 2 carbon atoms. First carbon atom, first pi bond between 2 carbon atoms, second pi bond also between 2 carbon atoms, because both the carbon atoms will have 2 unpaired electrons like this, even after hybridization.
Sir?
Okay. Yeah, tell me.
Sir, so here, basically, first the sigma bond is formed between 2s and 2p. So now there is no 2s left.
No, the exact way of putting it is 2s and 2px, right? 2s and 2px combine together to form 2 sp hybridized orbitals. And those sp hybridized orbitals form the sigma bond by overlapping with the carbon and hydrogen pure atomic orbital. So that is done, right? 2s and 2px are not there because they are already involved in hybridization to form a sigma bond. Yes, continue.
Yes, sir. Now py and pz combine with the atomic orbitals of C.
Correct. Another carbon atom. So py of one carbon, py of second carbon, pi bond. Pz of one carbon, pz of another carbon, pi bond.
Sir, but the number of carbons are C2, right? It's not C3.
Yeah. So what? Say, you see, right? Between the 2 carbon atoms only, I have 2 pi bonds, right? This is 1 pi bond, second pi bond, first pi bond, second pi bond, and 1 sigma bond.
And why are the pi bonds being formed only with carbon? It can also be hydrogen, right?
Oh, right. Now remember, for pi bond to be formed, right? For a pi bond to be formed, I can have p pi overlap. That is 2 p orbitals can have lateral overlap. Can s orbital involve in lateral overlap?
No, sir.
No. Hydrogen has only one s and nothing else, right?
Okay, sir. Yes.
Okay, right. Good question. Good question. Right. I hope everybody understands. It's a good question. Why is it that hydrogen is not able to form a pi bond? Not only in this case, in no case, hydrogen will form pi bonds. Okay. Right. So now we understood how the hybridization is, how the sigma bonds are, how the pi bonds are. Having a very bad cold. I'm sorry, guys. Okay. So now we went on to see how to determine the shapes or geometry of this molecule. And I told you that there's a difference between shape and geometry that we'll see later. Right. Now, for that, we have to go to VSEPR. We went to VSEPR. Right. So what does now? It's valence electron repulsion theory. Right. I think we took down the statement also. Right. So what the statement says is that, can anybody tell the statement? VSEPR.
So the molecule should be arranged in such a way that electrons will suffer minimum repulsion. Electronic.
Okay. Yeah. There should be minimum electronic repulsions. The shape of the molecule should be in such a way that there is minimum repulsions between the electrons. Yes, that's the exact way of looking into it. Right. Now, what kind of electrons are looking into? We are looking into electrons which are there. Okay. Electrons which are going to involve in bond formation, which are called bond pairs, right? And obviously, we are going to look into the electrons in the form of lone pairs. Okay, right? Fine. Now, we have to understand that the lone pairs are very big in nature, right? They're little not so localized. They're very much diffused, right? So obviously, when lone pair is there and another lone pair is there, lone pair repulsion is going to happen, right? And that is going to be maximum. Right. And always remember, bond pairs are little constricted, right? They are very tightly bound in between the 2 nuclei. So they will not have much effect. So that's why bond pair repulsion with the lone pair is a little lesser than lone pair, and obviously the least would be bond pair repulsion. Okay. Now, if at all you have bond pair and lone pair, obviously the first priority has to be given to lone pair repulsion only. Then only the priority has to be given to bond pair and bond pair, obviously, right? Whichever is the highest. If that is there, that only should be given the highest priority. Okay, right. Now, for all the sp hybridized systems, right? For all the sp hybridized systems, say beryllium chloride, we saw, or for say CO2, or say for C triple bond C and H, C2H2, right? When you have sp hybridized orbitals, and obviously you will not find any lone pairs also on the central atoms, most of the cases, right? So whenever you see that there are just 2 bonding electrons, right? Here 2 electrons are there, and here 2 electrons are there. Same way, here 2 electrons are there, here 2. Obviously here there are 4 electrons, right? So now what you see here, here 2 electrons are there, here 2 electrons, here 2. Obviously, this cannot be done. You cannot do anything with this, right? Because that is fixed. The triple bond is there. Same way. Okay. So all you have to understand is between this and this, right? And say between these 2 electrons and these 2 electrons, I have to make sure that the repulsions are minimum, right? Now, how do you make the repulsions minimum? How do you reduce the amount of repulsion? Obviously, by increasing the distance that is mentioned here. Okay, obviously by increasing the distance, right? Now, how do you increase the distance? Obviously, there is no much choice. Now, say, I think we already mentioned this. I can see here. The possibilities are, say, you can put chlorine like this, or say you can put chlorine like this, but eventually they'll be little close, right? The maximum distance I can have is only when I put them in a linear shaped molecule, right? And that's why we call these particular shapes as linear shapes or geometries. Doesn't matter for now, right? Now, why am I getting a linear shape geometries? Because only in this way, only this is the way possible for me to have minimum repulsion, maximum distance, minimum repulsion. Okay, right? And obviously, I told you that now the new thing we are going to introduce to you is your bond angle, right? Now, bond angle, I told you, you always take like this. Okay, now this particular point should be the central atom, bonding atom, and this point should be bonding atom. That is how you take, or anytime you take the bond angles. Okay, so now you see bonding atom, central atom, bonding atom. So this bond is what you take. Again, this bond is what, this angle is what you take, right? Same way you take bonding atom, central atom, bonding atom, this 180 degree. Same way, central atom, bonding atom, same way 180 degree. Like this only you take. Okay, right? So in a linear shape, if I have sp hybridization, the only possibility of the shape is going to be linear shaped. Because you can ask me, see, for steric number to be 2, right? I can have 2 possibilities. Either I can have 2 bonding atoms, right? Is it not? Like say CO2, beryllium chloride and all that, 2 bonding atoms I can have, or say I can have 1 bonding atom, 1 lone pair. Is it not? 1 bonding atom and 1 lone pair. That is also a possible case. And the third one is obviously going to be 2 lone pairs on the central metal atom. Obviously, that is not even a molecule, right? And you see that this is the only possibility. This is not even a possibility. There is no molecule. Literally, you can check. There is no molecule which will have 1 bond pair and 1 lone pair on the central atom, 1 bonding atom and 1 lone pair on the central atom, right? So I can blindly say the moment you find that the hybridization is sp hybridization, you can directly just go for the shape to be linear shape, and you can tell that the bond angle is going to be 180 degrees. This you can blindly say if you have sp hybridization. Obviously, if you have other hybridizations, you cannot say for sure. For the same hybridization, depending on how do I get the hybridization, like this, you see, like I had 3 choices here. Like that, when I go to higher hybridizations, higher number of choices will come, right? So for each of the choices, each of the permutation combination we can have, different shapes and different geometries will come. That we'll see later.
Sir?
Okay, yeah, tell me.
Sir, but geometry, it is going to be fixed, right, for a particular, because it is only determined by number of bond pairs, whereas shape is affected by both the number of bond pairs as well as non.
Absolutely, right? That is why for now we don't see the difference. Yeah, in very short time I will introduce you to what is the difference between shape and geometry. What you said is absolutely right.
Sir, so is it like geometry is the skeletal structure of the molecule?
Correct. I'll not introduce the lone pairs there. Meaning, even if I introduce the geometries, anyways, I will see. I will introduce you to. I'll introduce to everyone at a moment. Right. Okay. So we understood what is bond angle also. Right. Now what we'll do is we'll make a small table, people. Right. So, and you keep on filling this table as we progress. Right. Say I'm going to have a steric number, type of the molecule. Type of the molecule, obviously, okay. If I know the steric number, I know the hybridization also, right? They say fine. Steric number, type, shape of first is geometry, shape, okay, and I'm going to have bond angles. And I can even have examples. Okay, this table, a big table, maybe I don't know if you're using a long size notebook, right? An entire table, entire page should be required for this table. Okay, just make a table and keep. Okay, just make a table and keep. Right. So now the first entry we can include, say steric number 2 we saw, and the only type possible is AB2. You saw A is the central atom and B is the bonding atom, CO2, B is Cl2, C2H2. In that case, C2H2 case, one carbon, one hydrogen was there as the bonding atoms, right? So fine. So when you have steric number 2, the only possibility is AB2. And in this case, please just for now you write both the geometry and the shape are linear. Okay, both the geometry and shape are linear. Okay, and just now we saw the bond angle is 180 degree, right? Examples we saw CO2, beryllium chloride, C2H2, all these things are examples. Right? Okay, so as and when we see, we will come back and fill this table. Right? What is the time? How much time I took now for me to? Okay, I took 40 minutes. Anyways, it's good. This kind of thing we have to spend some time, or else you'll not understand. Okay, moving on, people. Moving on to steric number 3. Okay, steric number 2 we saw. Now we'll go to cases where we have steric number as 3. Okay, right. So steric number 3. Let me take the first example as BF3. Okay, now remember, the moment you have Sp3, the hybridization I think should come to your head. It's Sp2 hybridization. Okay, whenever you have steric number 3, obviously the hybridization is Sp2. Right? Now, we'll try to understand how this is having steric number 3. Right? Now, boron, right, doesn't have any lone pair. Right? Doesn't have any lone pair. Only 3 bond pairs. That is 3 bonding atoms of fluorine. So 3 plus 0 will become 3. So obviously it is Sp2 hybridized. This is done. Okay. Now we'll check how the hybridized orbitals are formed and so on and so forth. Right. Excuse me. So boron is having a configuration of atomic number 5. So it is going to be 2s2, 2p2 into 1s2, 2s2, 2p1. Total 5. Right. Now boron in ground state, right, will have, say, we have to take only the valence shell. So this is your 2s, this is your 2p. So 2s has 2 electrons and 2p has 1 electron. Okay. Now, obviously, when I go to the next, so not beryllium, boron, excited state, what will happen? One of the electron will shift to the higher energy level. Right? One of the electron will shift to the higher energy level. Now you will find that there are 2 electrons in 2p and 1 electrons in 2s. Right? Now you know what is the hybridization. I require one of the s orbital and I require 2p orbitals. So I take all of them, 1s and 2p's. I'll combine together to form 3 numbers of Sp2, Sp2, Sp2 hybridized orbitals, each having 1, 1, 1 electron. Okay. Now I'm going to have a sigma bond. Now the hybridization is done for the boron, right? Next, what has to come is the fluorine atom to form the sigma bond, right? Now the fluorine will form, will give 1 electron here, another electron here, and this fluorine will give another electron here to form 3 DF sigma bonds. Okay. Now hope you're all understanding how the hybridization came here. Right, I have P1, P2, P3, but only P1, P2 is having unpaired electrons, so that alone I take. And because that is what is the hybridization requirement. Right, so very simple. Now in this case, do I have any pi bond, guys?
No, sir.
Right, obviously now if, for example, I had an electron here, right, if I had an electron here, then obviously I would have told that this is going to form 1 pi bond. Because even after hybridization, I have still 1 unpaired electron, but in this case, there's nothing like this.
So it will form pi bond with which?
It will form pi bond with which?
Like which atom, which element?
That we'll see. In this case, it is not possible. We'll take a case where there's a possibility. Wait for it. Okay, in this case, it is not possible. In this case, no pi bond, obviously. 3 sigma bonds are there. Right.
Awesome.
Okay. Yeah, tell me.
Sir, then it would form sp3, right?
Not necessarily. See, just because I have an unpaired electron, it is not necessary that we have to take the entire thing, right? We have seen the case where, in the case of the other thing, say for example, you had 3 unpaired electrons, but you took only one of them. The other 2 are still there in the to form pi bonds. That is also a possibility. Just because you have unpaired electrons, it is not necessary that you have to take all of them. That is why beforehand itself we decide the hybridization by steric number. You understand what I'm trying to say?
Yes, sir.
Right? We decide the hybridization, take the required number and see what is left out. And in that left out, if you have any unpaired electron, then it forms a pi.
Okay, sir.
Right, good. So now, yeah, so in this case, there is no pi bond, right? Now let me take a case where I have a pi bond. Let me take NO2 minus. No, minus will work, or NO2 plus will work. NO2 plus, no, NO2 minus. NO2 minus if it's there. 2 electron, 1 electron. Yes, absolutely. Right. So I will take the example of NO2 minus. Maybe I'll give you a minute, people. I'll give you a minute to do exactly what we did here. Right. And just tell me, just do this. Just give the hybridization, the number of pi bonds, number of sigma bonds. Try to do this. I'll give you a minute. Quickly do it. And I already told you about negative charges, positive charges, where it should go for hybridization, right? Negative charge, it has to go to, negative charge has to go to which atom?
Central atom.
Oi, negative charge has to go to bonding
Negative
atom.
bonding.
bonded atom.
Sorry, ma'am.
Has to go
Sorry,
to-
sir. Negative.
Positive charge has to go to central atom.
Sir,
Okay, remember, positive central atom, negative bonding atoms. In this case, negative charge will go to oxygen. So what you understand is there are 2 oxygen atoms. One of them is having a negative charge. The other one is fine. The other one is normal oxygen. Okay. So if you're finding it confused and all, you can always draw the Lewis dot structure and then go forward with this.
Sir, is it 2 sigma bonds and 1 pi bond?
Yeah, I think it's correct. Right? Is it still having Sp2 hybridization?
Yes, sir. Yes, sir.
Okay, right, good. Guys, do me a favor, right? Whomever has finished it, the orbital diagram, whatever we did here and all that, just finish it and send it to me in WhatsApp. I'll check how exactly do we do it. I'm checking my WhatsApp. Complete the hybridization diagram for NO2 minus and send me in WhatsApp.
Sir.
Yeah.
Sir, actually, there isn't any need of drawing a diagram itself, right? Because if you find the steric number, then
Absolutely.
if you draw the
correct, exactly what you tell is absolutely true. If I know how to draw the Lewis dot structure,
you'll
and
get
I know how to find the hybridization, the job is done.
Yes.
But your school system is not like that, right? They require all this. Then only they'll give you a mark. That is why I am also telling you, or else if it is a JEE or NEET, I will not spend time on any of this. Right? But anyways, it is actually a very good thing to find the insights, right? Okay, from a new theory point of view, right? You are actually learning the inside out of the theory. That is good. That is good. Right? So yeah, whomever finishes, please send. I think I have so many people here, right? Oh, sorry. Right, I have 12 people with me. So I need 12. Let it be wrong, but all I wanted to just try. So 12 chats or 12 messages I must get.
Sir?
Yeah.
Sir, should it be like Lewis dot structure or?
No, the hybridization diagram.
Oh, okay.
If you want, you can always, whatever you feel comfortable, whether you started with Lewis dot structure, whatever you did, you just send me.
Okay, sir. I did Lewis structure, so only I asked.
Yeah. But I need the only Lewis dot structure is not acceptable.
Okay, sir.
Right? Lewis dot structure along with your hybridization diagram is what you have to send. Or if not, only hybridization diagram. That's fine.
Sir, how do we do it in hybridization diagram method?
Nothing. Wait, I'll again show you. This is what is hybridization diagram, right? You just show the ground state, show the excited state, and make the hybridization, make the hybridized orbital, see where the electron is coming from for the sigma bond and show it. And if you have any pi bond, mark it and tell that it is going to form a pi bond. That's it. So I hope everybody is doing it. Shailaja, Vaishnavi, Giridhar, Harshita, Tarush. I hope everybody is doing it. Madhumita, Subrajit, Ashwath, Ganesh, Hamsini, Srinidhi. Right? Come on. It really doesn't matter whether you're right or wrong. Right? I just want to see what you understood. Nothing else. It is not a test. You are not going to get evaluated. You are not going to get judged. Most importantly, right? Please send it. Right? Take a notebook and do it.
Sir, could you show the hybridization diagram again?
Sorry?
Could you show the hybridization diagram?
Yeah. Yeah, this is, maybe I'll make it small. Yeah, this is exactly the diagram. Mine is a little shabby, but you make it clean. I'm just finding it so difficult. Okay, see, this molecule I will do, right? It really shouldn't be taking this much time. It will hardly take a minute for you to draw it. That means you're not confident. So let me do it. Next molecule, you send it to me, but you try it. You keep on trying it, right? This molecule I will do, right? Fine. So now let me check whether it is going to have sp hybridization or not. I mean, first sp2 hybridization or not, right? So for that, I need to know how many lone pairs I have. Obviously, bonding atoms are fine. I can directly check 2 bonding atoms. Steric number is 2 plus what, right, is the question, right? Fine. For that, let me draw the Lewis dot structure for me to find out. Say nitrogen is having 5 valence electrons, 1, 2, 3, 4, 5, and oxygen minus, one of them is oxygen minus, right? Okay, so for it, it is going to have 7 valence electrons. Say 1, 2, 3, 4, 5, 6, 7. right? And because I told you the negative charge has to go to oxygen. One of the oxygen atom is going to have negative charge, the other one is going to be normal, right? Say 1, 2, 6 electrons, 5, 6, right? Now this oxygen requires 2 more electrons to satisfy its octet. This oxygen requires 1 more electron to satisfy its octet. So obviously you'll see nitrogen will take these 3 electrons, right? So now when you draw the structure properly, you will have a lone pair on nitrogen, right? There is a negative charge here. This is a negative charge. Single bond, double bond, and a lone pair on nitrogen. Okay, right? So obviously it has 1 lone pair. So the steric number is 3. So I'm going to have Sp2 hybridization. Very simple, right? Fine. Now we understood. So let me do it. So for nitrogen, 1s2, 2s2, 2p1. That is the atomic, oh no, 2p3, atomic number 7, right? So again, I take only the 2s and 2p, 2 electrons here.
Why 2p3?
Nitrogen has atomic number 7, right?
Oh, okay, sir. I took valence electrons.
Yeah, valence electrons only I have to take, but again, it's 2s to 2p3, obviously.
No, sir. I took 2, 2, and 1 like you did first.
Oh, okay, okay. That is for beryllium, right? Okay, right. This is for this thing. What is that? Nitrogen. Okay, now here I think I'm going to get something clumsy, right? I guess. Let me check. So nitrogen, this is in ground state, GS. When I go to excited state, right? When I go to excited state, what I understand is I'm going to have 1 electron in 2s, and say I can pair up. There is no 2D, guys. There is no 2D. So there is no place to shift the electron. There is no place. These 2 electrons are paired. Now there is no place to shift the electrons. So the only choice you have is to pair them up, right? The only choice you can have is to pair them up. Okay, right. Now all I need is Sp2 hybridization, right? We found out, right? This is going to have Sp2 hybridization, right? So all I need is 1s. Let me make it maybe in black. Let me mark the what is the requirement. So 1s and 2 of the p orbitals is what is required for me to form 3 numbers of Sp2 hybridized orbitals. Each will have 1, 1, 1 electron. Okay, obviously I'm going to have, I'm so sorry guys, I am so sorry. This is not the way we have to do it. I am so sorry. First of all, me asking you to do this itself is a blunder, right? Because I did not teach you where should you place the lone pair of electron. That's my mistake, right? Fine, guys, remember this. This is a good, anyways, we found this out. Right. Remember, we saw about sigma bonds, right? How do we form them, right? Basically, hybridized orbital with the atomic orbitals overlap, right? For pi bonds, we know where should you place the electron. Obviously, it is going to be between the atomic orbital and the atomic orbital. Okay. Now, one more thing you have to understand that when I have lone pairs in the central atom, right? When you have lone pairs in the central atom, remember that you have to place them inside the hybridized orbitals. Inside the hybridized orbitals. Very, 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 very important point. Okay. So we already know sigma bond. How is it formed? Pi bond. How is it formed? What about the lone pairs in the central atom? Right. Now remember that the lone pairs should be placed inside the hybridized orbital, right? And remember, for 1 lone pair, right, 1 hybridized orbital is required. Okay, for 1 lone pair, 1 hybridized orbital. Obviously, in a orbital, more than 2 electrons cannot be placed, right? Okay. Now what I understand is nitrogen is having a lone pair. Is it not? And now you understand why I'm even telling this point, why am I even mentioning this point, is that you see in the calculation of steric number, we take into account the number of bonding atoms and also we take into account the number of lone pairs, right? So from that itself is understood that the lone pair should be there in the hybridized orbital of the central atom. I mean, obviously, inside the hybridization is what you have to understand. Right now, so what you understand in this case is that nitrogen is having one lone pair. Right now, that lone pair should be inside the hybridized orbital. That means in one of the, I know I'm going to form sp3 means sp2 means 3 numbers of sp2 are there. I know that. Right now, in these 3 numbers, one of them is already filled. You get the point? And this already filled is nothing but my lone pair. Okay, so nitrogen is having sp2 hybridization. So I will form 3 numbers of sp2 hybridized orbital. And in this particular case, nitrogen is having a lone pair, right? So I told you that any molecule central atom having a lone pair, that should be placed in one of the hybridized orbitals, right? In this case, there is one lone pair. So one of the sp2 hybridized orbital will have a completely filled electron, like completely filled shell, right? That is going to have the lone pair. Obviously, the other two, right? The other two are going to have single electrons. Let me concentrate here. Okay, let me rub this part and write it again. Okay, right. Now nitrogen when goes to the excited state, right? All I have to understand is I'll make the 2s and 2p orbitals. Okay, now there is one electron. The second electron is going to shift, right? Now you have to make sure that the second electron goes here, or say here, either in this place or in this place. Why? Because obviously there's one more electron here, right? If you just shift. Why is it like this? Because when I take the hybridization sp1p2, two of the sp2 hybridized orbital are single electrons. Normal, these are going to involve in sigma bond formation. Right? Obviously, from the oxygen atom, one electron, they will get paired. Right? Done. That is sigma bond. But the third sp2 hybridized orbital is actually going to be a lone pair. The third hybridized orbital is actually going to be a lone pair. Okay, fine. Now what happens? Now we accounted for the sigma bond. 2 sigma bonds. You can understand, right? Where is the 2 sigma bonds? This is the first sigma bond. Second sigma bond, right? And we have accounted for one lone pair also. The only thing which you have to account for is this one, that is the pi bond, which is here, right? And obviously, what did I tell you? The number of pi bonds is equal to number of orbitals which are having unpaired electrons. Is it the statement complete? Is it the number of orbitals having unpaired electrons? Correct?
After hybridization.
After hybridization. Once I complete the hybridization, then you see how many unpaired electrons you have. How many ever unpaired electrons, that many pi bonds. Here there is one pi bond. Number of pi bonds in this case is 1. Okay, so the new thing you learned in this molecule is that if there is lone pair present on the central atom, right, you must place it in one of the hybridized orbitals. Right, and yeah, tell me.
Sir, that orbital with one unpaired electron will pair with will form a pi bond with which orbital?
This is my, say for example, pz, right? So the oxygen atom pz will come. They will laterally overlap to form pi bond.
Okay, sir.
Understood? Because I told you for sigma bond, what is the overlap? The overlap is between the hybridized orbital of central atom with the atomic orbital of bonding atom. That is sigma bond. For pi bond, atomic orbital, that is why you're not taking anything. We're taking the orbital outside hybridization. Outside hybridization is always going to be a pure atomic orbital. So pi bond is always between pure atomic orbital of central atom with the pure atomic orbital of the central, bonding atom.
Sir?
Yeah.
So that rectangle which you have marked, that shows hybridized orbitals, whereas the remaining one shows pure atomic orbitals.
Pure atomic. This is pure. Yes, absolutely.
Sir?
Yeah, tell me.
Sir, the pz orbital of one oxygen is forming a pi bond. Then what about the other oxygen?
Other oxygen atom means other oxygen atom has only sigma bond. In this case, you see, right? There is one sigma bond another sigma bond. We have accounted for 2 sigmas. Done. And there is one lone pair accounted for again in the hybridized orbital here. And there is only one more pi bond. And that we have accounted for in the form of this. Done.
Okay, understood, sir.
Understood? Right? Okay, we'll take one more example, people. One more example where I should have a lone pair. Yeah, tell me.
Sir, once can you write NO2 minus?
The structure.
No, sir, just the name NO2 minus.
Okay, NO2 minus. Okay.
Yes, sir. So here N should have N has 5 valence electrons. Correct?
Yes.
O2 means it should have 4 valence electrons.
O2 means, I don't understand. O2 means 4 valence
Like
electrons.
in the sense, for finding the number of lone pairs on central atom, we do this, right? We subtract.
Understood. Yes, we can do. But in this case, what is the
How to
problem
do in
is
this
I
case?
have, in this case, what
It
we have
didn't
the
work out
problem
for
is the
me here.
negative charge on oxygen.
Yes, sir.
That
I'm
is
getting
the only
0
thing.
lone pair.
If you know that O minus is always going to form a single bond, then you can again calculate, because for one O minus, one single bond, so 2 electrons will be gone. 1 electron is gone, and I know other oxygen atom will form a double bond, so 2 electrons is gone. So obviously the total number of electrons involved is 3, but there are 2 more electrons left. That is going to be in the form of lone pair. But again, all you have to understand is O minus will form a single bond, but oxygen atom will form a double bond. Okay, right?
Okay.
But it is always better to draw the Lewis dot structure and then come back to this. This is always better, advisable, because you will not have the confusion of finding out the number of lone pairs.
Sir, actually, I drew the Lewis dot structure without including the lone pairs. Still, I got 2 sigma bonds and 1 pi bond.
Without the lone pairs?
Yes, sir.
Did you take a coordinate bond?
No, sir. See, sir, like one single bond, so it has to be sigma bond.
Okay.
So, and one double bond means one is going to be sigma and one is going to be pi bond.
Obviously, right?
I did like that.
Can you just send me the picture?
Okay, sir.
Okay, right. So in the meantime, we'll look for another example for this Sp2 hybridization with a lone pair. Let me think about this. What about what should I take? Sp2. Why am I not getting any molecule? Okay, fine, not an issue. Maybe we'll see more examples in the maybe the other hybridizations. Not a big deal. Fine. Now, so there are 2 choices now. When you have Sp2 hybridization, that is when you have steric number as 2 people, right? Right. So when you have steric number as 2, right? The first possibility is that I can have AB3. Okay, the photo came. Even if that's the case, Raghav, obviously there should be a lone pair on nitrogen, right? Whatever the structure, you wrote it like this, the same structure which as I wrote here, right? So now 2 electrons are going from this nitrogen to this oxygen double bond, and 1 electron is going here. And obviously I have 2 more electrons left, right? There are 5 electrons left for nitrogen. Totally 5 electrons are in the valence shell. Do you get the point?
Yes, sir.
Okay, right, fine. So the first possibility of steric number 2, sorry, not steric number 2 people, steric number 3, I'm so sorry, right? So the first possibility is that I can have AB3 in the sense that all 3 of them are bonding atom. In the example of BF3, I can see all of them are bonding atoms, right? Okay, bonding electrons, whatever it is, right? The other possibility is that I can have AB2L. L represents lone pair. Okay, that means what? Steric number is 3. How? 2 bonding atoms and 1 lone pair. Again, we saw the example now, NO2 minus. Right. Now I just have to give one more good example I need to take. Okay, guys, just for the sake of understanding, let us take OSF2, OSF3. Is it right? OSF4. Okay, sorry. Okay, I have OS, but will I have any lone pair? Is the question. 4, 6. No lone pair. Okay,
No lone pair,
let
sir.
me wait. Let me take XCO3. Yeah, very good example. Okay, so I have XCO3, right? So now tell me first, you have to find out so many things, right? So first draw the Lewis dot structure for XCO3, right? And then find the steric number, right? And obviously find a steric number, you find the hybridization, right? Do the hybridization diagram, right? So in that hybridization diagram, to show sigma bonds, show pi bonds, show the lone pair, if you have any lone pair, obviously, right? Can you do all of these things, right? We'll come back to steric number 3 later. This is not steric number 3, people. So don't worry. This is not steric number 3. This is just for your understanding.
Sir.
Yeah, this is steric number 4. Absolutely. Yes. Draw the Lewis dot structure first, then only you can find the steric number, and then only you can find the hybridization, people, if you are finding it difficult. Xenon has 8 valence electrons. It belongs to noble gas family.
So then how does it form a molecule? It is inert, right?
That exact thing. This was not explained by your Lewis, right? Because it is already octet satisfied. But now I can, according to theory of hybridization, the electron can shift to the higher energy level, right? That is how xenon can form compounds. Yes, do you get the point? What I'm saying?
Yes, sir. Yes.
So remember, lone pair should be placed in one of the hybridized orbitals.
Sir, is it the same like last one? 2 sigma bonds and 1 pi bond.
So they will have, there are 3 oxygen atoms. So all the oxygen atoms will form a double bond, right? So there will be 3 sigma and 3 pi's. Okay, guys, I'll help you with the Lewis dot structure alone, right? Or okay, you don't even have to go for the Lewis dot structure. You can directly tell it from this. Totally, xenon has 8 valence electrons. Okay, now one oxygen atom, each oxygen atom forms double bond. Okay, each oxygen atom forms double bond, right? So now for one double bond, 2 electrons will go. For one double bond, 2 electrons of xenon, right? Now how many double bonds I have? I have 3 double bonds, 3 dBs, because I have 3 oxygen atoms, right? So can I say 6 electrons of xenon are gone, right? So totally 8, 6 are gone in the form of bond pairs. Obviously 2 electrons are left out, and that corresponds to 1 lone pair. That corresponds to 1 lone pair. I think it's very, very easy to understand, right? Xenon has 8 valence electrons. For each of the oxygen atom, 2 electrons will go, because oxygen forms double bond. It will give 2 electron, take 2 electron, right? So now each of the oxygen atom form a double bond. So now for each double bond, 2 electron will go from xenon. So I have 3 double bonds form 6 electron. So obviously there is 2 electron left out. 2 electron means 1 lone pair, right? Now, if at all you want to do it in the form of Lewis dot structure, again, you'll get the same thing, right? It's 8 electrons for xenon, 3 oxygen atoms having 6 electrons. Okay.
Sir?
Yeah, tell me.
Sir, so is it like 3 pi bonds, 3 sigma bonds, and 1 lone pair?
Exactly. Right? 3 sigma bonds, 3 pi bonds, and 1 lone pair. All you have to show in the hybridization. Right? So now each of the oxygen atom requires 2 electrons it took. Right? So whatever is given, it will be taken also. So now xenon has given 6 electrons, so it will take 6 electrons. Right? Now you see there is still a lone pair left. Right? Xenon, double bond, double bond, double bond, and there is still a lone pair left. Okay, right. So tell me, guys, what is the steric number here? 1 oxygen, 2nd oxygen, 3rd oxygen, 3 bonding
3 +
atoms,
1.
and there is 1 lone pair, becomes 4. So the hybridization is
Sp3.
Sp3.
Sp3. Absolutely.
Sir?
Right? Yeah, tell me.
Sir, why did you take it as double bond for oxygen?
Because I know oxygen's valence is 2. That's why.
So if the valence is 2 for every element, it will form double bond.
Definitely, definitely.
But then
Nitrogen,
in
you
case
see.
of NO2 minus, one oxygen formed a single bond with nitrogen.
But that was a O minus, right? Already one of the valence is satisfied by the negative charge. Do you get the point?
Yes, sir.
In O minus, what you're telling the oxygen atom, if I have, that's what, that is very, very careful, right? When you have oxygen atom and no electron, I mean, no charge, then it is then it is a double bond. If it is one of them is O minus, then definitely a single bond. Okay, that is what I mentioned last time also. Like whenever, I think, where did I mention? I would have mentioned O minus means single bond, oxygen atom means double bond. I should have mentioned it somewhere. Where did I mention it? I didn't mention. Okay, now you can take it on, people. O minus if you have single bond, oxygen atom means double bond. Right? So now always remember, if I have, for example, SO4 2 minus, right? Tell me there are totally 4 oxygens, right? Now this 2 minus, that means what? There are 2 O minuses and 2 oxygen atoms. That is what you have to remember, right? There cannot be O2 minus directly. You cannot do this unless and until it's an ionic compound. This will happen only in the case of ionic compounds. O2 minus directly.
Sir, for O2, sorry. Okay, sir, nothing, understood.
Right? Okay, so in this case, SO4 2 minus, you see there are 2 oxygen minus and 2 oxygen atoms. Same way, if I have NO3 minus, tell me how many O minus, how many oxygen atoms?
2 oxygen atoms and 1 O minus.
Right, 2 oxygen atoms and 1 O minus. Hope you're all able to. Same way in NO2 minus also you saw the same thing. 1 O minus and 2 oxygen atoms. Right, so there is only 1 negative charge means only 1 O minus. 2 negative charges means 2 O minus. Okay, anyways, now coming back to the XeO3 case, right? So we found out that in this case it is going to be Sp3 hybridization. Okay, now let me do it for xenon. Okay, fine. Now I think now you can do, right? Xenon, remember xenon belongs, okay, write the electronic configuration at least. Xenon will have 5s2, the valence electronic configuration will be 5s2, 5p6, 5d10. Am I right? Yeah.
So isn't it 4?
1 second. Helium, neon, argon, krypton, xenon. 1s, 2s, 3s, 4s, 5s. Yeah, 5s only. But is it correct is the question. So everything is filled. 1 second, guys. Oh, no. 5D is not yet filled. I'm sorry. Before this, 4D would have been filled, right? Before 5S, 5P, 4D, 10 would have been there. So we don't have to include it. So 5D, 0 is. Right?
Yes,
I should have 8
it's only
valence.
5s2 and 5p6.
Correct. 5s2, 5p6 and 5d, 0. Okay, right. Now you can do it. right? Now write the ground state, write the excited state.
Sir, how do we know if the element has an vacant orbital?
It's very, how will you not know? You know the electronic configuration, you know the atomic number. How will you not know whether it has an empty orbital or not?
So if the element has attained noble gas configuration, it will have a vacant orbital.
Not necessarily. We have seen previous cases also, which, like say in case of carbon dioxide, carbon is still having vacant p orbitals, right? Or in any case for that matter, you will have some way, you'll always have some empty orbital. If you don't have any empty orbital, then you can saw, if you saw in the case of NO2 minus, there was no space, right? There was no space, but somehow you will get all the requirements, even though it doesn't have any space for the electron to go. Right? You saw there are two sigma bonds which will come out, one lone pair will come out, one pi bond will come out. All things will be accounted for. You don't have to worry. If the molecule is reported, if the molecule, you know it is going to get formed, somehow you will be able to explain this. Don't worry. Whether it has an empty place or it doesn't have an empty orbital, it doesn't matter. Right? So anyways, so you have two electrons here, 6 electrons here, and no electron here. This is Xe ground state, GS. Go to excited state, right? Remember, in excited state, how many ever unpaired electrons you have, paired electrons you have, all of them should get unpaired. Shift all the electrons, right? Shift all the electrons.
Sir?
Yeah, tell me.
Sir, here can the electrons go from 5s or 5p to 4d?
No, it'll go to 5d. 4d is already filled, 4d10 already filled before this. Okay.
Oh, okay, understood. Yes.
Right. So now maybe this will help you guys. You will have.
Sir, but 4D10 won't come under the valence, right?
Correct. 4D will not come under the valence shell. Absolutely. That is the reason why we don't take it. And second reason is obviously it's completely filled. There's no place to put the electrons also. Okay. Now you would have shift 1, 2, 3, 4 electrons here, guys. Okay. Now remember what we got as the hybridization. Hybridization is Sp3 with 3 bond pairs and 1 lone pair. Remember this. How did you get Sp3? Is 3 plus 1. 3 is the number of bond pairs. 1 is the number of lone pair. Right. Now what did I tell you about the lone pair? Lone pair should be placed inside the hybridization, or it should be there in one of the hybridized orbitals. Right. So now you have to make sure that one of the electron is not here. It is actually going to be somewhere either here. Now, sorry, I have to put it like this. Right. Now, why do I put it here? Is because I require Sp3. So S, P1, P2, P3 will form 4 numbers. One of them is having the lone pair. The other 3 are having single electrons. So oxygen, sigma, sigma, sigma. One electron will get paired. Sigma bonds. Done. Now what do you have to account for? Now in the molecule, you see where is XCO3? You see there are 3 sigma bonds, 1, 1, 1, and there are 3 pi bonds also. Right. Now obviously what you see here, this after hybridization, I have 3 unpaired electrons, right? So obviously I'm going to have 3 pi bonds. Okay, right? So what again, I repeat step by step, generally what you do. You take the central metal atom, write the electronic configuration, write the ground state configuration. Then how many ever paired electrons you have, paired electron, pairing, unpair them. Put the electron to the next higher energy level. Right. Now, when you do this, next thing what you check for is the hybridization. And in the hybridization, do I have any lone pair or not? Right. If there is any lone pair, remove one of the unpaired electron. In this case, there was an electron here. I removed it and I paired it here because I require the lone pair should be there in the hybridized orbitals. Right. So there's one lone pair, and then you finish the hybridization. Finish the sigma bonds, then you go for pi bonds and then show the pi bonds also. How many pi bonds are there? Okay, right? Now say what is the time, people? I think we'll stop here. Maybe one more example we'll take, right? Maybe, and then we'll stop, right? And you are going to do this, right? I'll give you maybe 2-3 minutes time. We'll quickly do this. Let me go for I want something with a lone pair and a pi bond. Lone pair and pi bond. Lone pair and pi bond. Okay. XCOF4. Yeah.
Sir, does xenon have 8 electrons in its valence shell or 18 electrons?
8 electrons in the valence shell. 8 electrons. 18 electrons, we say generally 18 electrons, but those 10 electrons are coming from the 4D. So that is not included. Generally, we say it's only 8. Okay, inner d electron will be filled first and then the valence d electron, right? So that's how it happens.
Sir, if something has 18 electrons, we tell it has pseudo noble gas configuration, right?
If something has 18 electrons, then
In its valence shell, then it has a pseudo noble gas configuration.
Yeah, pseudo noble gas configuration.
So does xenon have?
No, xenon is a proper noble gas because it has only 8 electrons. 8 electrons in the valence shell. That doesn't have 18 electrons. 18 electrons, they generally say because they take the 10 electrons coming from 4D orbital, not 5D.
Okay, sir.
Okay. Right. Anyways, you do the exact same thing what we did. First one is steric number, and before that, obviously, number of lone pairs and bond pairs, and then you go for hybridization diagram, and then sigma bond, pi bond, and lone pairs. All of them you show. Where is it?
Sir, how do you draw the Lewis dot structure for this?
Yeah, very simple. Same way. Oxygen, exactly. You just try to draw it. Very simple. Oxygen, valency, fluorine's valency is 1, oxygen valency is 2. Very simple. If you maybe
so it will be like
not alone. Again, same thing. Xenon will have 8 valence electrons.
Sir, so 4 single bonds with fluorine and 1 double bond with oxygen.
Exactly. Or for all the fluorine atoms, single bonds, right? And one for the sole oxygen atom, 1 double bond will be there.
And lone pair is 2. Oh, sorry, 1.
1 lone pair. Yes, correct. Right. So now, okay, I'll take 1 oxygen atom having 6 valence electrons, 4 fluorine atoms having 7 valence electrons. Okay, I'll write another fluorine. And another 2 more fluorines. Okay, now this oxygen atom requires 8 electrons for its valence shell. 2 more electrons to complete its octet. This fluorine requires this 1 electron. This fluorine will take this 1 electron. This fluorine will take this 1 electron. This fluorine will take this 1 electron. Okay, right. So obviously, whatever electrons given will be taken by xenon also. Okay, right. Now what happened with oxygen alone? It formed a double bond with fluorine, one more fluorine, formed a single bond, and obviously xenon has still a 1 bond pair. Right. Now you can calculate this also because for fluorine I told you single bond, so 1, 2, 3, 4 electrons are gone, right? And here for oxygen double bond, so 2 electrons are gone. Totally 6 electrons are involved in bonding, totally 8. So obviously 2 electrons and 1 lone pair. Right? So again, the steric number would be what then? Now, steric number would be
5 plus 1.
Yeah, 5 plus 1. How is it 5 plus 1? 1 oxygen atom, 4 fluorine atoms, totally 5. And I just now found out that the number of lone pair is 1, so it becomes 6. What is the hybridization?
Sp3D2.
Sp3D2. 1 plus 3 plus 4. plus 2 will become 6. So it becomes sp3d hybridization. Sorry, sp3d2 hybridization.
Sir, actually, this is easier, sir, but the diagram is
Don't worry,
confusing.
don't worry. Very simple again. Right? So now for xenon, again it is going to be 5s2, 5p6, 5d0, right? So 2 electrons here, 2 electrons here, and no electrons in D. This is Xe ground state, right? Now Xe excited state. Now whatever be the paired electron, you just shift it to the next higher energy orbital. So 1 electron, 1, 1, 1. 1. Now how many? 1, 2, 3, 4. So you must get 4 electrons here. Okay. Now you form the hybridization first, right? Now the hybridization I know is going to be sp3d2, right? So you take s p1, p2, p3, d1, d2. Done. Right now, do I have now? You have to check whether I have any lone pairs in this molecule. Now I know that the XeOF4 has one lone pair. We just saw, right? This one is nothing but the lone pair. So now what should I do? I must remove this unpaired electron, right? And pair them anywhere here, any one of them. Say I pair it here. Anywhere I can pair. One of the hybrid orbitals should contain the lone pair. That's it.
Sir, can you repeat what you did?
Yeah. So what I did is there was one electron here when you shift it.
Yes, sir. 4
right?
electrons.
Now what I did is I did the hybridization. I know the hybridization is sp3d2.
Yes, sir.
Okay. Now in sp3d2, I found that there are 5 bonding atoms and 1 lone pair. Right? I have 1 lone pair
Yes,
present. I told you the lone pair should be placed inside the hybridization.
Yes, sir.
Right. So now I don't have any lone pair here. I have to have one kind of pairing. So what I did, I removed this one and say paired anywhere. Say I wherever I feel possible, anything. Say I paired it here. One of them is paired.
Sir, so while adding it inside the hybridized orbital, we have to remove 1 electron from a pure atomic orbital.
No, basically this is not a 2-step process. Basically, you must have had one lone pair in the hybridization itself. That's what you have to understand. Yeah, like if at all you want to understand it that way, say you remove the electron from the pure orbital and put it in the and pair it in the hybridized orbital. Yes, that also works. But okay, right.
Okay,
now
so
I have
now
yeah,
it will be 1 pi bond because only 1 electron is
exactly after hybridization. We have to account for only 1 pi bond, right? Only 1 pi bond is there. Only 1 pi bond between xenon and oxygen. So again, that is accounted for. This is my pi bond, right? So now I can draw 6 boxes. 1, 2, 3, 4, 5. One of them is having the lone pair. Done. All the others are having single electron. So I have 5 bonding atoms, right? That is basically 4 fluorine atoms and 1 oxygen atom. Each of them will give 1 electron to form 5 sigma bonds. Done. Right? So I've accounted for the sigma bonds, I've accounted for the pi bonds, I have accounted for the lone pair also, 1 lone pair which I have. Okay, right? We'll do more examples next class, people. Right?
Sir, can you show it once again?
Yeah, sure.
Sir, so for each orbital, we have to pair it, we have to mix it with 1 atomic orbital.
Correct. For each of the hybridized orbital, I have 5. This is done. This is already done. But for the 5 hybridized orbital, all these are sp3d2s. This is also an sp3d2, right? So now in the 6 sp3d2s, one of the sp3d2s has the lone pair, and the other 5 sp3d2s are responsible for 5 sigma bonds. That's it. That is, this hybridized orbitals will overlap with the atomic orbitals of 4 fluorines and 1 oxygens. Lateral, I mean, head-on overlap to form a sigma bond. Okay,
Yes, sir. Sir, and for p orbital, we know that the orbitals have three orientations like px, py, and pz.
Yeah.
Do we have any for d orbitals?
Yeah, d orbitals we have, right? I told you dxy, dyz, dxz, dx squared minus y squared, and dz squared. 5.
Okay, sir.
And we know shapes also for each of them, right?
Yes, sir. So xy here represents a plane.
Xy represents a plane. Exactly. Yes.
Done, sir. Thank you.
Okay. Right. I hope everybody understood. Can I get a yes from everybody? How did we get all this? Right. So now any molecule given, will you be able to identify sigma bonds, pi bonds, and lone pairs? Can I get a yes, guys?
Yes, sir.
Right. What about others?
Yes, sir.
Okay. Fine. I
Got
stopped
it, sir.
sharing. Right. I hope everybody finds it. Don't worry, guys. Even if you're little finding it difficult there and there, we will patch up. Right. We will little grow as we do more number of examples. Right. You will get better. Don't worry about this. Okay. But if at all, the only point is to keep on trying. Right. Only few more, like only 1 or 2 examples you find it difficult. But after that, once you find the knack, right, it's going to be very, very easy. Very, very easy. Okay, people. I think yeah, tell me.
Sir, we are gonna do more examples like this. Okay.
Yes, definitely. Tomorrow's class we'll do
Okay.
more examples. Yes.
Okay.
Right. Okay, guys. Any questions?
Sir, I'm not able to understand how do we find whether the element has a
Element has
1 minute, sir.
yeah.
Yes, sir. So how do we find whether an element has a vacant orbital?
Come again.
How do we find whether an element has a vacant orbital?
Have an empty orbital.
Sir?
How do we find an element will have an empty orbital?
Yes, sir.
That is very simple, right? All you have to do, say, if I have say carbon, right? Oh no, we'll not take carbon. Say for example, I take phosphorus, right? Now phosphorus, you will find that the valence electronic configuration would be 3s2 3p3. If you fill the electrons, nitrogen family 3s2 3p3.
15 group,
Right.
sir.
14. Nitrogen family 14 group. Yeah, correct. Okay, so now phosphorus will have 3s2 3p3. Now, since I have 3s and 3p, now the principal quantum number is 3. I obviously know that what is that? I can have a d orbital also. That is 3d can also be there, but it's just that the electron is not there.
How, sir?
What do you mean by how? The quantum, according to the quantum mechanical model, we studied quantum numbers, right? So if I have n is equal to 3, I can have L is equal to 0, L is equal to 1, and L is equal to 2. That means the d orbital is there. Whether an electron is there or not is the next question. Do you get the point?
Sir, can you once tell what does L represent? I forgot. Magnetic number?
No. Let's say when the principal quantum number is 3.
Oh,
Okay.
N is 3.
Now, n is equal to 3. Now L can be 0, 1, or 2. Correct?
Yes, sir.
N minus 1. 0
Yes,
to n
sir.
minus 1. Right? 0 corresponds to S, 1 corresponds to P, and
So
2
three
corresponds to
orbitals.
D. No. Not 2p orbitals. When I have 2, that means p orbitals are present. It can be 2p or 3p or 4p, doesn't matter. Again, it depends on the n value.
Yes, sir.
You get it?
Yes, sir.
So now if I have L is equal to 0, 1, and 2, 1 corresponds to P, 0 corresponds to S, and 2 corresponds to D. Right? That
Yes.
means in the third shell, I have a D subshell. Right? But electron is there or not depends on how many electrons I have in that particular atom. For in this case, for phosphorus, only 3p3, only 3p3, only till that much I have electrons filled. But say if I have 4 more electrons will basically get you to scandium, I guess. Now then you'll put 3d1.
Sir, so most of the elements will have a vacant orbital, right? An empty orbital.
Exactly. Most of the elements will have empty orbitals. Most of them.
When it will not have?
When will it not have? Maybe I'll look into some cases. Like generally,
So now we actually saw some problem like that, right?
yeah, we saw. That's what depending. Like say, even though I have some field, even though I have nowhere I can go, the electrons can go. There is no place for the electrons to go. But still, somehow, right? If I have one lone pair or two lone pairs based on that, I can still have bond formation. That is the entire idea about it. You will get a more, more insight and more grasp of it as we do more and more number of problems, right? So the thing is, for me to have hybridization, there is no, that is the requirement saying that I should have an empty orbital is not true. That is not the case.
Okay,
Right?
sir.
Even if I don't have empty orbital, I can have hybridization. No, that's the case. But again, those kind of cases are very, very few cases, right? Majority of the cases you will find that I will have empty orbitals and I will shift the electrons and I will do the hybridization. 99% cases, that is what you will see.
Yes, sir. Sir, so in last case, that is NO2 minus, the valence shell configuration of N is 2s2 and 2p3. Yes,
Yeah.
sir. So here N is 2. So
Hmm.
L should be 0 and 1, which is
Correct.
S and P.
Exactly.
And so D orbital is not present.
Absolutely. That is why we didn't shift the electron to the next 2D. We
Yes,
shifted
sir.
only to
We
the p
filled it
orbital.
in that section. Okay.
Exactly.
Okay, sir. Thank you, sir.
Right. Okay. Fine, guys. Thank you so much. Is there any other question anybody has?
Sir,
Yeah. Tell me, Kanna.
sir, how will they ask this chapter in MCQs? For this exam, we are having MCQs.
Oh, they will ask, like, say they'll give the molecule beryllium chloride. Find the hybridization Sp, Sp2, Sp3, Sp4, something like that. Right? Don't worry. We will solve questions.
Sir,
Or
is there
say,
any shortcut methods to solve all these?
yeah, shortcut way I told you, right?
We
Steric
already
number you
told,
can
sir.
find, then you can find the hybridization. Those things you use for the 1 marks, basically the MCQs. You don't go for the hybridization how I showed you, like don't draw the diagrams and all. Just go for the steric number calculation. 1 second.
Sir, is this chapter there in term 2?
1 second. There is so much noise around. Yeah, now tell me.
Do we have this chapter in term 2? No, right?
Do you have this chapter in?
Term 2.
I don't know. You must tell me. I think this chapter, once it comes in term 1, it will not be there in term 2, I guess. No.
Yes, sir. So it is going to be fully MCQ in term 1 also, right? So
MCQ is full. No, wait. Term 1 is full MCQ.
Yes, sir.
Yes, sir, fully MCQ.
So I guess no need to focus on diagrams, right?
Okay. This I didn't know. Thanks for the information. That way we'll solve more questions also, maybe then and there. Don't worry. I think it was Harshida, right? Who asked about
Yes, sir.
MCQs. Don't worry, Kanna. And now you told me that it is going to be only MCQs. We'll properly take care. From next class onwards, the teaching methodology will slightly change and we'll solve some questions also. Don't worry. Okay, Harshita?
Sir,
Yeah.
may I ask?
Yeah. Yes, Hamsini, tell me.
Sir, like from next week, will you be taking the new chapter, sir?
Next week, will I be taking a new chapter? No, I'll be continuing with chemical bonding only.
Okay, so I asked because I have like doubt in redox reaction balance.
You send me the question. If it, like I cannot teach you the entire chapter, but if you have specific doubts, you can always WhatsApp me, Kanna. I can help you there.
Okay, I have doubts in balancing, so yeah.
Balancing.
Yeah.
Okay, sure. You just send me.
Okay.
Whatever be the question, I'll help you.
Okay.
Sir, what is N factor?
Great question. N factor. Again, that will take another 1 hour. I mean, at least half an hour for me to tell you what is that. We'll see in some other class. Basically, it comes in equivalent concept. How do you have mole concept? There's something called as equivalent concept. Okay, so there we use it. I'll tell you maybe once we go for redox reactions, that time it might be necessary.
Yes, sir. I read it in redox reactions.
Yeah, we will see it there. No problem. Very
sir,
simple.
is it related to the number of moles something?
No, it is related to for an element, it depends on the valency. For an acid, it depends on the number of H plus. For a base, it depends on the number of OH minus.
Yes, sir.
For a redox reaction, it depends on number of electrons lost and number of electrons gained. So many, depending on the molecule, depending on the reaction, the N factor will change. We'll see all that. Don't worry.
Okay.
In detail, we'll see. Okay. Any other questions? Anybody has?
No, sir.
Okay, guys. Thank you so much. We'll meet again tomorrow.
Thank you, sir.
I'm ending the
Thank you,
class.
sir.
Thank you. Yeah.
Thank you,
Thank you,
sir.
everybody. Thank you. Thank you.